for the first regular session for this morning. The first speaker is going to be Takuma Yoshioka, and he will be talking about abstracting effect systems for algebraic effect handlers.
Hi, everyone. I'm Takuma from Kyoto University in Japan. The title of our paper is Abstracting Effect Systems for Algebraic Effect Handlers. First, I introduce algebraic effect handlers briefly as a background of our work. Algebraic effect handlers can represent some computational effects, such as mutable states and exceptions or others. They have two components, operations and handlers. They are similar to exception raising and handling, but they have difference from them. They can resume the computation after operation calls. This is a program that uses algebraic effect handlers to implement mutable states. In the handled expressions, put and get are operations that write into or read from one mutable cell. And the below is there's a handler. This handler implements the behavioral put and get. And then this program evaluates to 42. However, there's unhandled operations, which is similar to uncalled exceptions, cause runtime errors. In this program, there's no handlers for put and get. Then this program is a stuck down. It gets stuck. And to prevent such runtime errors statically, effect systems for algebraic effect handlers have been studied. They statically track unhandled operations as effects. We do not effect as epsilon, and then they guarantee that every operation is handled appropriately. For example, I show an effect system that uses sets to represent effect. In this derivation, the premise expression put 42 and get unit had the effect put and get. This set means operation put and get are not yet handled. And in the conclusion of this derivation, we install the handler for put and get. Then this handling expression has empty set. The empty set means every operation is handled. So this is an example of effect system. So there's several ways to represent effect. So such various effect representation, such as set, as I talked in the previous slide, have been studied. For example, in this table, I show sets, simple rows, and scoped rows. These various implementation of effects are motivated by, for example, type inference on improving expressive power. The difference between simple rows and scoped rows is whether the duplication, the operation in one effect is allowed or not. And rows are a sequence of operations. So this is our research question. What are essential commonalities or differences among various effect representations? This unknown relationship suggests that there's no guide for language design and we will create a new style. So to tackle this problem, our approach is abstracting effect representations. We define effect algebras to abstract effect representations and give instantiations from it. And provide lambda calculus over effect algebras. We call it lambda EA. And to prove the soundness of lambda EA, we define safety conditions. If concrete effect representation meets the safety conditions, then we can immediately read the soundness of such instance. I summarize the contributions of our work. First is effect algebras. They abstract the effect representations and their manipulations. Second contribution is lambda EA. This is a lambda calculus with effect handlers. Importantly, it is parameterized over effect algebras. Third is safety conditions. The requirements on effect algebras to prove the soundness of instances. As a main theorem, we proved that any instance of lambda EA is sound if it meets safety conditions. So I talked more detail about our work. First topic is effect algebras. Before introducing the definition of effect algebras, I show an abstract target. They are manipulations of effect representations. In this slide, I show the manipulations of set representations. First manipulation is operation injection. First is a typing rule for operation calls, and this rule injects the operation OP to the singleton set. The second manipulation is sub-effecting. Sub-effecting over-approximates the effect. In a set of representations, sub-effecting is inclusion. The third is operation removing. This is a typing rule for effect handlers. Then effect handler in the effect system, effect handler removes the operations from the effect. In this rule, handled expression E has the effect epsilon. And handler for OP removes the operation OP from epsilon, and as a result, we get epsilon prime. Then the whole expression has effect epsilon prime. So we abstract these manipulations by effect algebras. And this is a definition of effect algebra. Effect algebra is a tuple, O, E, up arrow, O dot, and 0. O is a set of operations, and E is a set of effects. And up arrow is a unary operator from O to E. We use this as operation injection. And O dot is a binary operator to concatenate two effects. This operator concatenates two effects into ones. And at last, the 0 represents the empty effect. So important point of effect algebra is that the E, O dot, and 0 forms a partial monoid. For example, an effect algebra for set representations is as follows. The operation injection is an operator making singleton. And the effect concatenation is union in set. And the empty effect is empty set. So we define a typing rules based on these effect algebras. And first is the operation calls. We use upper arrow operator to inject the operation to the single effect. This upper arrow OP corresponds to the singleton set for OP in the set representation. The second typing rule is sub-effecting. We use this symbol circled less than to represent sub-effecting. This relation is defined as follows. And important point is that we use O dot operator to represent this sub-effecting. And this sub-effecting relation corresponds to inclusion in the set representation. At last, and the typing rule for effect handlers, we use O dot operator to represent operation removing relation. This is correspond to the union in the set representations. Okay, and next we briefly talked about lambda EA. Lambda EA is a lambda calculus parameterized over effect algebras. Its supporting features include explicit polymorphism and deep effect handlers. And not supporting features includes bounded row polymorphism or other handling mechanisms, such as tunneling or lexically scoped handlers. So to prove the soundness of our calculus, we define safety conditions. The safety conditions are requirements on effect algebras to prove the soundness. There are two conditions. The first condition is no operation satisfies this relation. The intuition is that sub-effecting cannot erase the information about operation calls. Please recall that right-hand side, the zero symbol represents the empty effect. So by this, if we allow this sub-effecting, we can arbitrarily erase the information about operation call. The next second condition is as this: if the effect epsilon has information about operation OP, and we remove the different operation OP prime from E and get the remaining effect epsilon prime, then the remaining effect epsilon prime also has the information about operation OP. The intuition is that handler for OP prime can only remove the operation OP from an effect. By this condition, we can exclude the undesired operation removing like this. So there are sufficient conditions. So we prove that as a main theorem. The statement of theorem is that any instance of lambda EA is sound if it meets safety conditions. This theorem suggests that safety conditions formalize a common nature of sound effect systems. Then we know that all we need to do when considering new style of effect representations is to check that instance meets these safety conditions. As a corollary of this theorem, we proved that instance of lambda EA for EFF links and COCA in the literature are all sound. The proof are as follows. Their effect representations meet the safety conditions. In other words, we provided another way to prove the soundness of the existing effect systems. So I summarize this talk. There are several styles of effect representations, such as sets, simple rows, and scoped rows. Then we abstract these effect representations by effect algebras, and provided lambda EA over effect algebras. And to prove the soundness of lambda EA, we define the safety conditions. As a contributions, we show contributions in these 4 items. First, effect algebras. They abstract the effect representations and their manipulations over them. The second contribution is lambda EA. This is a lambda calculus with effect handlers parameterized over effect algebras. The third contribution is safety conditions. Safety conditions are requirements on effect algebras to prove the soundness. As a main theorem, we prove that any instance of lambda EA is sound if it meets safety conditions. I briefly show other contributions of our work. We adapt our calculus lambda EA to shallow handlers, and this change does not affect the safety conditions. And furthermore, we also make two language extensions to lambda EA and gave additional safety conditions for them. I omit the details about the extensions. The important point is that our additional safety conditions for these extensions reveal the essential differences among various effect representations. Thank you very much for this talk.
All right, we have time for some questions. And while we do so, if the next speaker can already come up and set up. Yes.
Hi, thanks for your talk. Hello.
Oh.
Hi there. I'm Simon Peyton-Jones. Thank you for your talk.
Hey.
So what you've done is by abstracting out these effect algebras, you extract out the sort of common features.
Yes.
That's very nice. So what sometimes happens when you do that is you say, okay, now I've got 3 examples, and now I realize the thing they all have in common. I can make 4 and 5 and 6.
Oh.
So I wondered whether you had come up with other effect algebras that you might then, as it were, plug back into Coco or Links to get a slightly different language, and what that would tell you. You know, can you explore the world of effect systems in a new way?
So I omit this slide, but we provided a multi-set style effect representations in the paper, and the difference between sets and multi-set as captures as additional safety conditions. Then we, as I say, we can give another style of effect systems, but novel style of effect system. The multi-set extension is very simple. So very complicated, but crucial style is not found. At least our work.
Okay, thank you.
Yes, over there.
Thank you. I'm Hideki Kawabata from Hiroshima City University. Maybe I'm misunderstanding, but you used the concatenation operation. You defined your concatenation operations using examples of union.
Yes.
But there are many other kinds of representing ways, like treating effects as a set of sequences. Not just sets, but sequences. In those situations, can your framework apply?
In that case, we define append in list operator as a concrete as an instance of O dot.
Append, but append just affects one sequence, not the sequence of set.
Set of
sequences.
Set of sequence. I cannot understand what you say. What is the set of sequence?
I mean, there are several effect systems treating not just set of effects, but set of sequences of effects. So the element is sequence of effects in that case. So just concatenate, just appending something to another thing is not appropriate, I guess.
Sorry for interruption. So I'm a co-author of the paper. So I think we can implement such a new effect algebras. I think, yeah, just concatenations or concatenating over each element and sets over sequences can be implemented a union, and each element can be concatenated. So I think it's possible.
Okay, thank you.
All right, we have to stop here and move on. But let's thank the speaker again.